Hello friends, today's question: a wooden cylinder of diameter 4r, height h and density, this has to be rho by 3, is kept on a hole of diameter 2r of a tank filled with liquid of density rho as shown in the figure. So this is a basic figure. So we have a wooden cylinder. Here it is shown as a square, but if a wooden cylinder we can redraw the figure again also. So we have to solve these three questions based on this particular description. So first is, now the level of liquid start decreasing slowly when the level of liquid is height h1 above the cylinder block starts moving up. At what value of h1 will the block rise? So it means, so this is the height of the liquid above the block, that is given h1, and we have to find out the value of h1. So in this, all these questions, you can see all these three parts, the important is the balance of the, or you can say equilibrium of this particular block. And for that we have to find out all the forces which will be acting on this particular cylinder, and we are going to balance them, or so that everything comes in equilibrium, and then we are going to solve the question. So let us redraw the figure and draw it in the form of cylindrical. So this is your cylinder, and this cylinder is placed on a wooden block or a block type system, and this block type system is something like this. So this is the level of the liquid, and above the cylinder it is given as h1, and h is the height of this cylinder, and it is said that the wooden cylinder is having a diameter of 4r, so its radius will be 2r, and it is kept on a hole. So this is a hole, and the diameter of the hole is given as 2r. So in this case, this radius of particular hole will be equal to r, and this entire is filled with a liquid. So this is a basic diagram for the given question. And in the first part, let's first of all try to find out what will the various forces acting on this cylinder. And in order to find out the various application of the forces, obviously there will be two prominent forces. One will be the weight that will be acting in the downward direction of the cylinder, and another will be the buoyant force that will be acting in the upward direction. And through this hole there will be also a atmospheric pressure that will be acting in upward direction to the cylinder, and from the top there will be also a atmospheric pressure. Okay, so these are the forces that will be acting on the cylinder. So you can say that the cylinder will be in equilibrium when forces due to pressure, and weight balance out. Especially in order to find out the pressure, we should be knowing the area of all the, you can say we should be knowing the area of this surface cross section, we should be also knowing the area of this particular hole, which is with respect to the cylinder, and we should be also knowing the area of the remaining part, which is in the bottom except this hole. So first of all, let's find out what will be the different types of areas. So you can say the top cross-section area, let us call that A3. A3 is area of cross-section of the cylinder. Area of cross-section of cylinder, and that will be our radius is 2, so this will be coming as our A3 will be equal to 4 pi r square, and next let us find out our A2. A2 we call the area which is associated with this particular hole for the cylinder. So we say area of cylinder with respect to hole, and that will be equal to our pi r square. So the area which is left, or we can say which is in contact with the water. So we just found out the area of this hole, and we know the area of this cross section. Now we are interested in finding out what will be the area of this which is in contact with the liquid, and let us call this as A1. So we say A2, that is area at the bottom submerged in liquid, or we can say, yeah, it's given liquid, so let us write liquid only. So A2, so obviously A2 will be equal to 4 pi r square minus pi r square. This gives us 3 pi r square. So we found out all the respective areas that will be used in order to calculate the pressure, which will be giving us the force. So like I said, the cylinder will be in equilibrium when the forces due to pressure and the weight balance out. And so we can say this balance involves considering both pressure due to water, considering both pressure due to liquid on the submerged part, on the submerged part of the cylinder, comma, weight of the cylinder itself, and atmospheric pressure. And atmospheric pressure. So let us write the force equations. and for that we start with our A3, and A3 is our this top portion. So let us draw this A3. So this is our A3, and the liquid that is above this A3, it is given as H1, and there will be also atmospheric pressure, and let us call this as PA. So it means the force is going to have two parts, one with the liquid column that is above this particular A3 area, and another one will be the atmospheric pressure. So we can say pressure at the depth H1 from the top of the water, sorry, let's say given liquid, acts on the submerged area A3, acts on the submerged area A3, or we can say the cross-section area of the cylinder. Cross-section area of cylinder. So we can say force due to this pressure, force due to this pressure, and let us call that FA3, which will be equal to atmospheric pressure PA, atmospheric pressure plus liquid column of height H1, liquid column of height H1, and this whole multiplied by the area A3. So we substitute all these values, we get FA3 will be equal to atmospheric pressure is PA plus height pressure is given a rho G H1, and this is multiplied by A3. So this is our first pressure equation, or we can say force equation. Next is our weight of the submerged portion that will be acting downward. Weight of the submerged portion of the cylinder So this is our cylinder. I'm drawing a small one, and the entire weight will be acting in the downward direction, and this is our, you can say, call this as WA3, and the height A of the cylinder is given as H. So we can say WA3 will be equal to our mg, and we can write this as volume multiplied by density is given to us as rho by 3, multiplied by G, and volume we can write it as A3 multiplied by H. Therefore we get WA3 will be equal to A3 multiplied by H rho by 3 multiplied by G, and this is our weight equation. Now next is our, you can say, force due to the air exposed portion, means due to this hole. So you can say force due to air exposed path, or we can say hole at the bottom. And this is the entire cylinder, and this is the part of the cylinder which is with respect to the hole, and its area we said is our A1. So we can write, and here it will be the atmospheric pressure acting in the upward direction this way, because it is an open hole. Therefore we can say that atmospheric pressure acts on the area A1 Therefore the force let us call that FA1 will be equal to atmospheric pressure multiplied by A1. And last is the buoyant force that will be acting in the upward direction at the, you can say, bottom of the cylinder. So this is our top, and this is our bottom of the cylinder, and we have a hole something like this, and above it we have a liquid height is given as h1, and the height of this cylinder is given as h, and the, you can see, upthrust will be acting except this portion, cause, and it will be acting here, and we call this area as A2. So we can say that pressure at the depth of H plus H1 at the depth of H plus H1 acts on the submerged portion A2, acts on the submerged area A2. So therefore let us call that force as FA3 rather. Force FA3, it will be equal to the atmospheric pressure and the, you can say, liquid column height at H plus H1. So we can write this as atmospheric pressure plus liquid column height H plus H1, and entire thing multiplied by A2. So we simply substitute the values. We get FA3 will be equal to PA plus rho g h plus h1 and multiply by A3. So we found out all the respective forces that will be acting on the, you can say, various areas of the cylinder. So we have three areas. One is the entire cross section, which we called as A3. Another one is the weight of the cylinder acting in downward direction. Next is the upward due to the atmospheric pressure only in the area which is associated with this hole. And the last one is you can say the pressure at the bottom of the cylinder except this hole. Now we are simply going to equate all these force equations. So we can say, for here we can say at equilibrium, downward force will be equal to upward force. Will be equal to upward force. So we put the downward force because of area A3, the weight that is associated with A3, or we can say entire cylinder, and we have force because of area A1 plus force because of area A2. Now we simply substitute all the respective values. So we get this as PA plus rho g h1 multiplied by A3 plus A3 multiplied by H, and we have here rho by 3 multiplied by G is equal to PA multiplied by A1 plus PA GH plus H1, and this whole is being multiplied by A2. And we already know the values of A1, A2 and A3. We substitute them. We get PA plus rho g H1, and A3 was our 4 pi r square, and here also 4 pi r square multiplied by H rho by 3G. This is equal to PA multiplied by A1, and A1 is our pi r square plus PA, and we have here rho G H plus H1 multiplied by A2, and A2 was our 3 pi r square. So this pi r square, pi r square, pi r square cancels out throughout, and we open this bracket. So we get this as 4PA plus 4 rho g H1 plus this becomes our 4 by 3 H rho g is equal to PA plus 3PA, and here we have 3 rho GH plus 3 rho G H1. Now here it is 4PA, and here is also 4PA. So these two terms cancels out, and we can write this as, here we have 4GH1, and here we have 3GH1, 3 rho GH1. So we can write this as 4 minus 3 rho GH1, and here we have 3 rho GH, and this is 4 by 3 rho GH. So this becomes 3 minus 4 by 3, and we have rho GH. Rho GH cancels out. So this gives us that H1 is equal to, this becomes 9, and this becomes 5 by 3 times H. So we get H1 in terms of H, and if we check the options that are given to us, option number C is the correct option for that. So we can say option C is correct. Now we come to the B part. First of all, we try to understand what is the difference between these two figures. So in this figure, you can see that above the cylinder there was a liquid column, whereas above the cylinder there is no liquid column, only air is present. So this is the first major difference. And the height of the liquid is given to the, you can say, S2, which is slightly less than the height of this cylinder. Okay, so these are the two major differences, and because of this, the equation, once again we are going to use all those equations which we found previously, but with the difference is that the area or the top cross-section area is now going to have only the atmospheric pressure on it. There will be no liquid column pressure. So this is the first major difference, and the rest of the difference we can clarify when we are going to solve it further. So we can write the equation. So let us, you can say, part B. And we have a, you can say, cylinder, which is something like this. The hole is same, the area associated with this hole will be also same. The only difference is now the liquid is about something here, and this height is, yeah, it is given as H2, sorry, that height is given as S2. So height up to here is given as S2. So this was our A3, and this area associated was our A2, and this area was our A1. I think I have written it correctly. A2, sorry, this is our A2 and this is our A1. So we can write the equation similarly. There is no, so I'm going to start from directly from here. At equilibrium, downward force will be equal to upward force. We can say at equilibrium there will be only atmospheric pressure that will be associated with A3. So this is our PA. So we get from here PA multiplied by A3 plus, and next is our, you can say, rho by 3 GH multiplied by A1, and next is our, you can say, PA multiplied by A2 plus PA plus rho G H2 multiplied by A3. I think, yeah, this looks good. So we substitute the value. I think there is there was small error on my part. Okay, I corrected it. So this is PA3 plus rho 3 and multiplied by A3, PA1, the atmospheric pressure because of here, and then it is, you can say, and multiply by area A2, that is only this part. Okay, so now it's correct. So we substitute the value PA and multiply by A3. A3 was our 4 pi r square plus rho by 3 GH, and multiply by 4 pi r square. We have PA multiply by A1. A1 is our open area, that is our pi r square, plus we have here PA plus rho G S2, and multiply by our A2, and A2 is our 3 pi r square. Let me write it here. This is our head area A3, and this is our atmospheric pressure due to atmospheric pressure, and this is our weight. And this portion is our because of the area in contact with the hole. Area in contact with hole, that is atmospheric pressure, and this the last one is because of the, you can say, liquid column of height H2. Liquid column due to height S2. Next is quite easy. Here our pi r square cancels out throughout once again, and now we just open the brackets. So we get this as 4PA plus we have here 4 by 3 rho GH, and that will be equal to PA plus 3PA plus 3 rho G H2. Once again, this is our 4PA and this is our also 4PA, so this cancels out throughout, and we get this as 4 by 3 rho GH will be equal to 3 rho GH H2, and this rho G and rho G cancels out, so therefore we can say our H2 is equal to 4 by 9 times H. So the options that are given to for part B is our 4 by 9 times H, which is option number A is the correct option. Option A is correct. Now we come to the last part, and here it asks that if the height H2 of the water level is further decreased, then so we have these four options. So it means if we further reduce the height of below this level H2, then we have to find out what will be the position of our cylinder, whether it is going to move up, move down, or it is going to remain same. And if it is going to move up and down, so we have to find out that particular value of H2. Okay, that is H by 3, H by 4 or H by 5. Or A part is it is going to remain at original position. So this portion we can say we are going to analyze this for H2 is equal to 4 by 9H, and at this particular value of height of the liquid we are going to analyze the forces. So in this case it is only asked whether it is going to move up, or you can say move up or original position. Only two conditions are there. and this is only going to happen, it is going to move up when the buoyant force is on the higher side as compared to the weight, and it is going to remain at the same position if the weight is greater than the buoyant force. So we have to check only this condition, and whichever comes true, and that is going to give us the answer. Okay. So let us find out the buoyant force. Buoyant force, let us call that FB, and that will be equal to our pi r cube multiplied by, we have this height is 4/9 h rho. So this is the amount of the buoyant force, and next is our weight of the cylinder. Weight of cylinder, let us call that W, and that will be equal to 4/3 pi r cube multiplied by h multiplied by g. So if you make the comparison between the buoyant force as well as the weight of the cylinder, so let me write it. So we can write this as 4/3 pi r cube h multiplied by g, and sorry, not equal to, but we have here 4/3 pi r cube, and we have here hg 4/9, sorry. So from here we can clearly see that the weight of the cylinder is on the higher side as compared to the buoyant force. Okay, you can say weight of cylinder is greater than the buoyant force. So under this condition, the cylinder will remain at its original position. Cylinder will remain at its original position. And the options that are given to us is option number A is the correct one. Option A is correct. Okay. So this question was a lengthy one but quite easy, and everything was on the based on only on the about you can say forces, the balance of forces, which results in the equilibrium of the entire cylinder. This completes the question. Thank you. Sorry, there was some major calculation problem on the part C. So let me do it again. So we are going to analyze the forces at the height h2 is equal to 4/9 h. So let us start with the, you can say, the weight of the cylinder. And which we also calculated previously, and that was A3 multiplied by h rho by 3 multiplied by g, and we know A3 is our 4 pi r square. So this becomes our A3 is our 4 pi r square. 4 pi r square h rho by 3 multiplied by g, and if we rearrange them, we can write this as 4/3 pi r square rho h g. So this is the weight of the cylinder, and let us calculate the buoyant force. And we call that FP, and FB will be equal to density of the liquid is given as rho, and that will be equal to the, you can say, the volume that is associated with the liquid, and the only portion of the, you can say, which is associated with the liquid is given as H2. So we have this as A2 multiplied by H2 multiplied by G. So we substitute the value, we get buoyant force will be equal to, we have rho, and A2 we already know, A2 is our 3 pi r square, and H2 and H relationship we know, H2 is 4 by 9 H multiplied by G. So this goes by 3. So we can write our buoyant force will be equal to 4 by 3 pi r square, and this is a rho Hg. So if we compare our weight and buoyant force, so let me write the weight as 4 by 3 pi r square rho Hg, and buoyant force is 4 by 3 pi r square rho Hg. So we can clearly see that these two values are equal when our H2 is equal to 4H by 9. Okay, this condition holds true for 4H by 9. And if the height is further reduced, so because this holds true for H2 is equal to 4 by 9H, and the H2 is only available in the equation for buoyant force. Now if we reduce the value of H2 below 4 by 9H, you can say if H is, or we can say H2 is less than 4 by 9H, this will result in the reduction of the buoyant force. This will result in the decrease of buoyant force. So if for any value which is true for this relationship, the buoyant force will be reduced, and under this condition the weight will be on the higher side as compared to the buoyant force. And we can say under the condition whenever H2 is less than 4 by 9H. So therefore the further reduction in the height of water, that is H2, therefore any further reduction in the level of water, level of liquid, that is S2, the cylinder will not move. The cylinder will not move and remain its original position. Remain in its original position. So we can say option number A is the correct one. Option A is correct. And in this equation, you can also see that I have not used the atmospheric pressure, because you can say for this the solution of part A and part B, we clearly concluded that ultimately the atmospheric pressure is going to cancel out. Okay. So that's why we have not used the atmospheric pressure in this equation. We are only you can say considered the buoyant force and the weight of the cylinder, because the atmospheric pressure we have seen that it always cancels out. From here, like we see, this is 4PA and this is PA plus 3PA, so this ultimately cancels out. So that's why we are not included the atmospheric pressure in these calculations. So I'm sorry for that. I made a big mistake in this particular solution. Hopefully now it's correct one. This completes the question. Thank you.